Hello, I'm Patty Simpson with Simpson Math. Let's use the normal distribution and central limit theorem to help us find z-scores. First, in an Oreo factory, the mass of a cookie is a normal distribution with a mean of 40 grams and a standard deviation of 2 grams. We want to know what is the z-score for a cookie that has a mass of 43 and 4/10 grams. So let's first look at this distribution that this cookie belongs to. So this population of cookies, if we were to weigh or find the mass of all of those cookies, we create a distribution. It would be a normal distribution with a mean of 40. So remember, our mean is here in the center. In a normal distribution, your mean, median, and mode are at the peak, at the right in the middle, and they're the high point. Then we can count by this standard deviation of 2 grams. So above the standard deviation, at 42 grams, that's 1 standard deviation above the mean. We say that the z-score of our mean is 0. We're right at the mean. The z-score for 42 is 1 because that's 1 standard deviation above the mean. I'm going to add another standard deviation on there so that we're sitting at 44 grams. That is 2 standard deviations above the mean, so we say that z-score is 2. I'm going to do that one more time, add a standard deviation, so add 2 on, and that z-score, or that is 3 standard deviations above the mean. Now I'm going to go below the mean. If I count back 2, I'm sitting at 38 grams. This is 1 standard deviation below the mean. The z-score for this is a -1. That negative tells me that it is below the mean. It's below average, and it's 1 standard deviation below that average. Count back another 2 so that I'm at 36. The z-score for that 36 is a -2 because it's 2 standard deviations below the mean. And then 1 more standard deviation, and I'm at -3 because that's 3 standard deviations below my average. Now, if I wanted to draw this distribution, put in my inflection points there at my standard deviations, and remember that it's symmetric and it has this bell shape to it, so that the normal distribution looks something like this. And this particular cookie that we've randomly chosen from here has a mass of 43.4. That mass is somewhere in here. And we want to know what is the z-score, or how many standard deviations above or below the mean is this mass, this 43.4, that data value. Well, if I were to look on here, I can see that 43.4 would be somewhere in between here. 43 should be halfway, 0.4 a little bit over. So this is a data value that's somewhere in there. And I want to know, what's that z-score? How many standard deviations away from my mean is that? Well, it's 1 and a little bit. To find out more precisely, we can use that z-score formula that just says I take my data value, I subtract my mean, and I divide, so I find out this distance, and then I divide by this width, so I divide by my standard deviation. I'm going to do that here. My data value is that 43.4 grams. I'm going to subtract my mean to find out how far away it is. And I'm going to divide by this width of 2. We know that our z-score is going to be positive because our data value is above the mean. And it should end up being 1 and a little bit, just by looking at where it's sitting. So let's see if it really is. 43.4 minus 40 is 3.4. That's that distance from here to there. Divide that by the width of 2. Well, 2 goes into 3 one time with 1 left over. My decimal remains. 2 goes into 14 7 times. So the z-score for that particular cookie is 1.7. In other words, this cookie is 1 7/10 standard deviations above average. Now, let's look at this. Here we have a sample of 64 cookies that was collected. The sample mean of 39 8/8500 grams was collected. So in other words, we collected 64 cookies, we found the mass of each of those cookies, and then we found a mean for those 64 masses, and that mean was 39 8/8500 grams. We want to know what's the z-score for this sample mean mass of the 64 cookies. Now notice this is a different value than this data value over here. Here I am just looking at the mass of each cookie. Here I have collected a sample of 64 cookies, looked at those masses, and then found a mean of those masses. That mean is different from just a mass of a cookie. This mean belongs to a different distribution. Let's draw that distribution. Now we know from the central limit theorem that this distribution of sample means, called a sampling distribution, is also approximately normal. The central limit theorem tells us that it is going to be an approximately normal distribution. The central limit theorem also tells us that the mean of this sampling distribution of sample means, so the mean of this distribution of these sample means is equal to the mean of the population. So it's going to be equal to this same 40 grams. So here in the middle, my 40 grams is still my mean. That is also going to be the peak of this, just like it was before. My mean, median, and mode are right there in the middle. But my standard deviation for this sampling distribution of sample means is a little different. Remember that we take the population standard deviation and divide it by the square root of the sample size to find the standard deviation of our sampling distribution. That's what the central limit theorem tells us. So my standard deviation was 2 grams, and I'm going to divide that by the square root of my sample size of 64. So I have 2 divided by, well, the square root of 64 is 8, or that is 1/4, or maybe you could call that 25 hundredths. You could either just do 1/4, or you could call it 25, this is equal to 25 hundredths. 1/4 is 25 cents. So I'm going to count up by the standard deviations. So 40 and 25 hundredths grams is 1 standard deviation. So the z-score is 1 standard deviation above the mean, whereas my mean is z-score is 0. If I add another one of those, I'm at 40 and 5/10 or 50, 25 cents, 50, if you think money. So that z-score is 2 standard deviations above the mean. Add another 25 hundredths, and you're at 40 and 75 hundredths grams. And that is 3 standard deviations above the mean, so the z-score would be there at 3. I'm going to count backwards a standard deviation, so I'm subtracting 25 hundredths. So I'm at 39 and 75 hundredths. That's 1 standard deviation below the mean. To show that, I call that z equals a -1. That negative lets me know that we're below average. Then I subtract another 25 hundredths off of there, and we're at 39.5. The z-score there would be at -2, because that's 2 standard deviations below the mean. And one more of those, and I'm at 39, 25 hundredths and 25 hundredths. And that's a -3 is its z-score. So the distribution that this particular sample mean belongs to looks something like this. We know it's normally distributed based upon the central limit theorem. We know that it has the same mean as its population, but that its standard deviation is smaller. So I want to know what's the z-score for this mass. Well, 39 and 85/100ths, if I look at that, I can see that that particular data value would be somewhere between 39 and 75/100ths and 40. Somewhere in here is that data value. And I want to know what is that z-score. Well, we can tell already that that z-score is going to be negative because it's below average. And that z-score should be less than 1 because it's not even 1 standard deviation below the mean. I'm going to use that same formula I used over here where I have x minus the mean. But notice that when I found the standard deviation here, the way I found that standard deviation was I took my population standard deviation and divided it by that sample size. So because I'm dealing with a sampling distribution, to find my standard deviation, I had to do the standard deviation divided by the square root of its sample size. So here I'm going to fill in. I have 39 and 85/100ths is my data value. My mean was 40. And once I did this part, once I did this little formula, I found that my standard deviation was 25/100ths. So now I do some subtraction. 39.85 minus 40. Remember, really, you're just doing 40 minus 39 and 85/100ths to get 0.15. But because this one's bigger and it's negative, it stays negative. Divided by 0.25. So now do a little more subtraction here. The way I like to do this is I like to just simplify my decimals or my fractions. First of all, if I'll multiply the top and the bottom by 100, I just end up with negative 15 over 25, and then I don't have to worry about those decimals. Then I'm just going to simplify my fraction. If I divide the top and the bottom both by 5 over 5, then I have negative 3 over 5. This fraction is the same as that fraction. Or to make it into a decimal, you could say times 4. Here I would have to do times 20 over 20. Either way, I'm going to get a negative, because it's negative, 0.6. So if we make that into a decimal, this would be the fraction if I wanted to count by fractions, or it's just a negative 0.6 or 6/10. Think of it as times 2, and you can see that better because that'd be tenths on the bottom and a negative 6. So negative 6/10. So the z-score for this one is negative 6/10. Notice that this one is closer to the mean. This z-score tells me that it's closer to the mean. It's below average because it's negative, whereas this one is further away from the mean. And we can see that it's further away from the mean. But because this one's positive, it's above average. So the z-score tells us a little bit about our data value. It specifically tells us how many standard deviations above or below the mean that data value is. And also notice that when it was just one cookie that I was pulling out, then that one cookie was part of this distribution, this normal distribution. But then when I pulled out a sample and found a mean from that, it created a sampling distribution. And in order to find that standard deviation, I had to take the standard deviation of my population and divide it by the square root of my sample size. So the central limit theorem is a really powerful theorem that lets us create these normal distributions using that information from our population. Math Made Simple is Simpson Math. Thanks for watching.